Right.
All right, so welcome everybody. Ben is with us tonight. He is going to do day 21 of the 2021 Advent of Code called Dirac Dice or Dirac Dice. I'm not sure how it's pronounced. But it is honestly, the first part seems pretty easy, and then the second part is honestly one of the hardest and most fun problems that I've ever done in AOC. So I'm super excited to see how he solves this problem. So take it away.
All right. So day 21 Dirac Dice. So let's read the problem first. So there's not much to do as you slowly descend to the bottom of the ocean. The submarine computer challenges you to a nice game of Dirac Dice. This game consists of a single die, 2 pawns, and a game board with a circular track containing 10 spaces with 1 through 10 dice. Each starting space is chosen randomly, which is your puzzle input. Okay, let's just take a quick peek at my puzzle input. Okay, that's really short. All right. So players take turns moving. Okay, so yeah, 2 players. Each player's turn, the player rolls the die 3 times and adds up the results. Then the player moves their pawn that many times forward around the track. So moving clockwise. Spaces of increasing value, wrapping around to 1 after 10. Okay, so you can think of using modulus and stuff now. So if a player is on space 7 and they roll 2, 2, and 1, so that'd be 5, move forward 5 times the spaces. 8, 9, 10, 1 is stopping on 2. So yeah, 7 plus 5 is 12. Mod 10 is 2. Okay. After each player moves, they increase their score by the value of the space their pawn stopped on. Player scores start at 0. First player starts on space 7, total 5. Stop on space 2, add 2 to score. Got it. Game immediately ends as a win for any player whose score reaches 1,000. Okay. So first game, it's a practice game. I would assume that's the first part of the problem. Submarine opens compartment, play deterministic dice. 100-sided die falls out. Die always rolls 1 first, then 2, then 3, and so on up to 100, after which it starts over at 1 again. Right, so play using this die and use your puzzle input. So just example game input here. Example solution. All right, so what we want is we need to find the moment each player wins. So the score of the losing player times the number of times the die was rolled. All right, so let's just make a deterministic die. So I'm going to use a kind of cool feature of Python, which is iterators, well, technically generator expressions, which are functions that instead of doing like return X, you do yield X. And then the next time you call the function, the state of the function is still preserved, which is nice because we want to have the next number be rolled for each roll of the deterministic die. So I'm going to say die value starts out at what, 1? All right, here we go. So you got that, and then we have challenge here. Okay, so it starts out at 1. Yep. Yeah, roll 1 first. Okay, so die value equals 1. So what we want to do is, actually, I'll just start at 0 for convenience. So for the deterministic die, we're going to do global. We can store the die value globally, like irrespective of the function's call. And then we are going to, I mean, it doesn't really need to be generic expression when written this way, but I'll just do generic expression, whatever. So die value can get put in here. What we want is while it never ends, we are going to yield die value. First increase die value plus 1 and then yield die value. So let me think about this. Yeah, it's easier to just make it a function actually. Okay. 0, we'll increment die value and turn die value. Range, and I'm just going to do min die value, just a little sanity check. Okay, run all. No, it's called dead die. Of course. That is not working because there. All right, that's definitely not working. That's working. So that's what we should get for our deterministic die. Then we want die value actually to equal die value plus 1, and then mod that by 100. Because every time die value reaches 100, it just rolls 1 again. So this actually won't work if you just modulate it by 100, because then when die value reaches 100, it will go back to 0. So what we want is I think we want die value. I think we want die value mod 100 plus 1. Let's just check this just for fun. So I run this 101 times. That's going to eventually get me back to 1. All right, that's perfectly fine. So now we have 2 players. So I'm just going to have P1 player pause. I'm going to make this a tuple. So the Python immutable right thing of the player starting positions, which actually is our input. So player 1 starting input is 4 and player 2 is 8. So 4 and 8. And then we also need player scores. So I'll start out at 0. And then player take turns moving. So I'll just do turn equals 0. And then we do I'll do while. So while the max player score is less than 1,000, because once it is equal to 1,000, players have won. So after this, players won. Some players won, which we can figure out. So while nobody's won, we're going to have whatever the turn is play. So after that, we're going to do turn equals turn plus 1. And this we can actually just do a modulo because we want 1 or 0. Modulo 2, because when it reaches 2, you want that back to 0. So we want, so player pause. Just make these arrays for simplicity. Right. So we want player pause. Turn is why I have turn via integer, not just some like Boolean or whatever. Because then I could just use it to index these arrays. So we want the position. First, we need to roll the dice. Roll equals set die. And then we just want to add 3 of those together, because we have to roll the dice 3 times. So 1, 2, 3, move to space time. Right. So we want player position plus roll. Well, player position turn actually do this. Position is 1 plus 2 plus 3, which is 6. We start with 4. So is there a position 0? No. Okay. So we're going to need to do that same thing. So we want player position turn plus roll minus 1, I think, mod can. And that should get us the position on the board. We'll do player score turn plus equals player position. So that's how that works. So it's probably not going to work. And then we do print score. Oops. Okay, there we go. 1,001, 722. Is that right? It's probably not right. Right, so player 1 has at least 1,000 points. Yep, that is not right. So I'll just do some quick debugging. So we want to print player pause turn and then player score turn. Just so we can follow along with roll in there. Just to follow along with the example that they gave us. Which is a very common debugging. Okay, so 6 doesn't move to space 10. That's wrong. Because I forgot to do that. There we go. Maybe that's right. So 6, 10, total score of 10, and then total score of 3, space 3. Okay, that's relatively right. Now we can do print. Just do player scores. Don't need that anymore, hopefully. 1,745. That is right. So losing player has 745 points. So we'll just do the minimum of that times. Okay, so then we need to know how many times the dice is rolled. Just do n rolls. And you know what? I'll just do it in here. And we can just rolls plus equals 3 because we roll the dice 3 times every time that gets rolled. So 7, 3, 9, 7, 8, 5, 7, 3, 9, 7, 8, 5. All right, that's right. So let me just plug in my puzzle input, which is 5 and 9. There we go. I get 9, 8, 9, 3, 5, 2. Hopefully that's right. And there we go. That was part 1. That's not so bad. Well, the catch is it's day 21, not day 1. So there's got to be something fishy going on here. So part 2. Now that you're warmed up, that's very, very encouraging. It's time to play the real game. The second compartment opens, this time labeled Dirac Dice. Out of it falls a single 3-sided die. Well, that's interesting. As you experiment with the die, you feel a little strange. An informational brochure in the compartment tells you that this is a quantum die. When you roll it, the universe splits into multiple copies, 1 copy for each possible outcome of the die. In this case, rolling the die always splits the universe into 3 copies. One where the outcome of the roll was 1, one where it was 2, and one where it is 3. Okay, so that's interesting. So, the game is played out the same as before. Although to prevent things from getting too far out of hand, the game now ends when either player reaches at least 21. Okay, so this is an interesting problem. Now we're no longer just playing a simple game. Now we are having to simulate all possible outcomes of a game. However simple the game is, there are a lot of outcomes to this game. See, player 1 wins in a ridiculous number of universes. So we're going to have to do some sort of optimization to solve this problem, which I'll get to later. But, so that's part 1. Part 1's done. Part 1 is pretty much irrelevant at this point. Aside from the basic rules of play of the game, it's pretty irrelevant. So what we're going to start out with is we're going to have, again, just have player pause and player score. This time I am going to use tuples for a reason also that I'll tell you later. Well, actually, I'll just tell you now. Because tuples in Python are hashable, so you can store a tuple as a key of a dictionary, but you can't store an array as a key of a dictionary because the Python quirks. Anyways, so if we have 3 dice that can roll 1, 2, 3, okay, so that would get you a number from 3 to 9. And because we're measuring the number of outcomes, I don't think we need to simulate all possible rolls of all the die, because then that would be 3 different rolls for each die. So that'd be 27 possible outcomes per turn. But I don't think there are actually 27 different outcomes because we only care about the sum of the 3 rolls of the dice, which can only be from 3 to 9. So we're going to still actually, because since this branches, this is a recursion problem, because for every game, it splits into more different scenarios that are reliant on the current state. So I'll just do def play. It sounds very ominous here. And then I take scores. Actually, I'll just take positions and then scores. So what else should I take? Positions, scores. I think that's enough information for the state because we have position and score. And we, oh, turn, yeah, duh. Turn equals 0. So for each, this play function will just simulate a single iteration of the game, a single level of the game in the giant tree that is formed from this sort of bifurcating universes. So we're going to have, again, the roll, except for this time, we don't have roll equals something. We're going to have for roll in range. So 3 to 10, I think that'll work. Because we need to simulate all possible rolls for this current positions and scores in this game and the turn. All right. So for roll in range, we're going to have the same sort of thing. So we're going to have new pause equals positions, and then new scores. And I'm just going to convert these to lists again, so we can just mutably index it. Right, there we go. And then yeah, we can just do the term when we call the function. So again, we still need to, we have the role, we have the position, and we have whoever's turn it is. So we're still going to do just, new pause and then turn plus equals roll. Except for we don't do plus equals roll. I'm just going to copy this here. There's a bit from part 1 we can use, just not the same strategy. Right. Plus roll minus 1, mod 10 plus 1. Okay. And then we're going to do new scores. New scores. Spell. New scores. Turn plus equals new pause turn. Okay. So that is playing a single turn in essence. But now what we need to do is we need to see if that player won. So that is another state that we need up here. So this play function is going to, the top level call of this function will return which player won each amount of times. So we're going to just have a little player wins in here. Actually, we should have passed that as an argument because it needs to. Does it? No, it doesn't. Doesn't need that. So we'll have player wins equals just an array starts out at 0, and then when it'll return the wins, so we'll be able to add the wins on. So what we're going to do is we're going to have wins from here. So these will be the wins that happen for all the games that happen past this current point in the game, which is our current state with whatever roll it is. There will be, again, I think, not 9, 6 of these happening. And then the wins from here will be, again, we're going to recurse now. So play, and then we want tuple, new, pause, and then tuple, scores, and then we want turn plus 1, mod 2 to get the next turn that needs to be played. And then we're going to have, actually what I'm going to need to do in here is this doesn't happen all the time, because if a player wins, they've won, the game is over. So if max new scores is greater than, it's greater than 21, it is at least 21, so greater than or equal to 20. Then we're just going to do player wins, and then to find out which player, we'll use a kind of cursed Python ternary here. So 0 if new scores 0 is greater than new or scores 1, else 1. So if player 1, player 0's score is greater than player 1 score, player 2 score, it won. So player wins equals 1. Player 1, end of story. Otherwise, nobody did win. We're going to need to play some more. And then we're going to have to do, the player. Just going to use list comprehension here, actually. No, I won't. It's easier not to. Do wins from here. Player wins 0, and then just copy that over. All right. I'm sure this is not going to work. There's no chance. So wins equals, just going to play. Then we need our starting positions, which I have. Actually, I'm just going to plug in these 4 and 8 for debugging reasons. So play, player pause, player score. Okay. All right. So this is taking some time, and then it broke, which is not surprising. So maximum recursion depth exceeded in comparison. So we are not having a good enough termination condition because this thing is going out of control. So is there an example in here? No, there's not. That's very helpful. So let's see what we did wrong here. Play tuple, new position, new scores. All right. So what did I do wrong? Wins from here. Okay. Getting the error again when we do play here. So turn +1 mod 2. Okay. Go back to the problem type. Game ends when each player reaches at least 21. I'm just going to print the scores. Make sure we're not just dumbly exceeding 21. Okay, we're not exceeding 21, but it's not doing so well. So, I'm doing this right. No, obviously I'm not doing it right. New positions turn. New scores turn is positions. Wondering if maybe, yes, unlikely. I think the interpreter might have its version limit limited artificially, but I don't think that's true. Let me just find out. Version limit is usually 1,000. All right, so okay, let's just try this. Probably a bad idea, really bad idea. Probably not going to work. Oh, it is working. Sort of. It's a ridiculous number. Will it just run until it breaks? Probably. Probably not good for my memory. Oh well. Yep. Okay. So something is obviously going wrong because we shouldn't need to use that. So, oh yes, that's why. Because I made a really dumb mistake. Because I need to return the player wins here. So this is going to keep going for its quality time because it needs to count a lot. Except for it doesn't. Because it reaches that limit again. That's just great. Let's see if that keeps going. If that keeps going. That's great. It doesn't. Wouldn't surprise me. Yeah, Maximum recursion depth. All right, so let me just see when someone wins. Hello, Jerry. All right. Yep, nobody's winning. I am definitely doing something wrong. Okay, so we have list positions, new pause, new score. Player wins a 0, roll in range 310. +1, that's doing that right. 3 rolls. We don't care about number of rolls here. We do care about player position and score. Sure, +1, odd 2. Okay. Actually, you know what, I'll just, now that's irrelevant. Maximum new score is greater than. Yep, that should work in theory. But again, it's not. We reread this yet again. 3 copies. You know what? Why don't we just do it the actual way to make sure that something's not going seriously wrong? We're summing the dice. Yep. Okay. That may have forward 3 times and adds up the results. Okay, just for fun, let's do that. So instead of doing for roll in range 1, I'm just going to do for dice 1 in range 0, 0 to 3 plus 1. I think that should do it. 42, 3. Okay. And I'll just print 2, sanity check. Make sure I'm not doing anything seriously wrong. Should add 1 to those because 0 to 3 will give us 0, 1, and 2. Just sum that up. Okay. That work. Oh boy. Yeah, that is going infinite recursion. That's not supposed to happen. Obviously. What are we doing wrong again? So if it moves 3, the first player moves 3 points and they have 6 points. So that should scores. Okay. So if they roll, yeah. So they start out at position 1, roll 3, 4 points. I don't think that's quite right. Yeah, oh yeah, they start out at 4 plus 3 would be 7. So that does make sense. That doesn't make sense. Does it? Yeah, it does make sense. Okay. Okay. So let's see if we just, so let's do some optimization here. If we memoize it, does that solve our problem? Tools.lru cache max size equals none. So this will create a cache of our function's output. So if the function is called the same arguments, it will just return the value that previous function returned without actually calling the complex function. And I'm still getting maximum recursion depth errors. Oh, something is going seriously wrong here. That's what it is. Of course, I'm going to make stupid mistakes. That is honestly what most of my time spent on Advent of Code problems is stupid errors. Actually, just for an example, let's run it without the cache here, because that was pretty quick. So if I run it without a cache for every split in the universe, it's going to play all the possible outcomes. And it's going to take your computer a very long time to tabulate all these wins. Because what is it? It's like a ton. It's still running. Let's just kill that. So now if we memoize it with functools.lru cache, it's pretty fast because there are a lot of times that the same state in the game is reached by different previous things that happened in the game. So if the players have the same positions and the same scores, it'll just reuse the result from there on, which saves a ton of computational time. Just for fun, since that worked, I'm not going to put it in yet. I'm just going to demonstrate what memoization is for people that don't know. So if we do def memoize, we are going to, it's going to take a function as an argument, and it returns a function. So let's do there. So we're going to do def memo f. Okay. And that is going to be a function that takes some arguments. So it takes in a function and returns another function. But the thing that it does is it has a cache, which is a dictionary. And so we're going to do arg tuple equals tuple args. So if the arguments are already in the cache, argument tuple in cache, it's just going to return what's already in the cache. Now, if it's not in the cache, it's going to call the function that you supplied. So that's the result. And then before returning the result, it's going to stick that result in the cache. And then it's just going to return result. So all functools.lru cache is the exact same thing as this function. It's just a function that returns another function. But Python has fancy syntax for this. So you can just put a little @ symbol and that above your function. And oops. If there we go. There we go. That should work. Nope, that did not work. Of course it didn't work. It's got scores. Yes, because we need to unpack arguments. So this again is a little Python notation that is basically for variadic arguments. So it just takes that, compacts all the arguments that you call the function with into an array. And this takes that array and kind of, again, unpacks them as arguments to a function. See, we get that same result really fast. Whereas if we don't memoize it, it's just going to keep running and running. I think the first time I solved this problem, I actually didn't do this because I was using Rust, which runs faster, and it still took its quality time to run. But it's a lot more time than if you just make a simple optimization. So let's just plug my input in here. So 5 and 9. Hopefully all this work isn't for nothing and we'll get the right answer. So let's just make sure that that's actually one. How many in player that wins in more universes? Yep, okay, first player. There we go. All right. That's the right answer. So hope you enjoyed. Hope I didn't go too fast or gloss over anything. Yeah.